If you have mass transport limits from the atmosphere, what are the area requirements for the scales of carbon dioxide removal that we need?
Well, yes, you have mass transport limitations. You roughly need, if you can pass air at 1 meter a second through a filter box, if you think of it that way, you need about 60 square meters of cross-section for 1 ton a day of CO2. So the world would need, at 36 gigatons, 100 million such units. These are container-sized. Shanghai Harbor processes 30 million, and we park 1 billion cars. So you have the room to do this, and you're actually much smaller than the windmills, which, if you think of making fuels, the windmills which produce the energy to make the fuels are bigger than the air capture devices. Compared to a tree, your uptake rate per day is roughly 1,000 times higher.
So the first barrier that you mentioned, Sally, for CCS is cost. And I've got a bit of a chicken and egg question about cost. My somewhat limited understanding of what the oil and gas companies and related engineering firms have done is that they seem to have put a big emphasis on R&D maybe over the past decade, but drawn down those programs. And at least in limited conversations I've heard, they've emphasized that in the absence of a carbon price materializing, they drew down their R&D. So if you think about, okay, well, maybe we need to wait for a price on carbon to make CCS happen, or we could prioritize R&D to drive down what the cost would need to be, which could actually make a price on carbon feel more feasible. So in your long-term view, how do you think about this interaction between, are we really needing to wait for a price on carbon to motivate R&D, or should we be taking another approach?
I think that we need to find a way to deploy more projects quickly. And it could be that for the first 10 projects that agree to, to do this, that they could, for example, be compensated at the social cost of carbon. And because it's my view that there's only so far we can go in the lab with these technologies, particularly the newer technologies, because the systems concepts are going to be fundamentally different. So if you looked at just a better amine, it's not that big of a deal to stick a better amine into a existing system. But some of these new capture concepts, the whole systems need to be tested. So I think we need to get more deployments at scale where we can begin to get the real technological learning that allows us to optimize. One of the things you find is that because of the uncertainty in performance parameters, that there's a lot of over-design, which drives a lot of cost. So I think that's the first thing we need to do. I think I think R&D is really important, and we should continue doing that. And after we get these, say, first 10 or next 10 projects in the pipeline, I think we need to be thinking of that in the context of, okay, well, so what year do we absolutely need to put a price on carbon so that others follow quickly? And we've been going through this very sort of lumpy, approach. There'll be a tranche that are developed, and then nothing happens, and so we need to smooth this out so we can get on the rapidly rising deployment curve. So I hope that answers your question.
I have a question. Oh, go ahead.
Good question.
Well, I have a question also for Sally, and it's associated with novel cycles for the power production that may be especially amenable to carbon capture. And some of these things include like recycle loops from fuel cell anodes, which have a concentrated CO2 stream already, and for which no energy penalty or very small energy penalty is associated with carbon capture and storage. And for the last 20%, if we could put those kinds of systems onto the coal plants and have them contribute to this very low cost of capturing the carbon, I think that would be pretty neat technology to explore.
Yeah, you're absolutely right. And the big announcement was about, 3 months ago, ExxonMobil announced that it was going to have a collaboration with direct carbon fuel cell or direct,
Correct, fuel cell energy.
Right, yeah, from fuel cell energy. Very, very exciting. So you're actually making energy in the process of separating CO2. Yeah, I'm very optimistic and very excited about the electrochemical cycles.
Cool, thank you.
can add a little to this. You heard Sally say that the cost of retrofitting is going to be high in terms of electricity costs. I'm probably an extremist in this, that I think those plants are stranded assets, even if you make optimistic assumptions about capture in a flue gas, because it's just too high. So you end up doing exactly what you said, and I was 15 years ago working at the Zero Emission Coal Alliance we had formed about exactly doing fuel cell designs. And back then that was a bit premature and got caught in one of those earlier cycles where people say, well, Bush said no Kyoto, so everybody said goodbye after they just said it's a very interesting technology, we should put in $50 million. So we need to think about the bigger systems issues, and I would argue you want to go there. You also want to think about other ways of sequestration. It's not just geological. You can form minerals, you can form bicarbonate minerals dissolving into the ocean. But you need to have the alkalinity if you go that route. You can also, I mean, the biochar discussion is out there. Right? I'm not very friendly to it because I feel we put something which is not in the thermodynamic ground state outside, waiting for it to find its thermodynamic ground state, and then we horribly failed. And that could be CO2 if it's aerobic and methane if it's anaerobic. Either way is not very nice. Yeah. Right? And we could also hide things in the infrastructure. People have suggested if we go to carbon fiber, but 10 billion people would put roughly 50 tons per person into the infrastructure before we paid back our old debt. So that's the challenge.
So Sally, part of the premise of this this conference here is that we've electrified everything that can be electrified, and many of the CCS technologies assume we haven't electrified. So my particular passion is strategically, as we're deploying and revising the energy systems around the country, whether it's for campuses or cities, whether we should be building, new gas facilities, because it is a step better than coal, but then it locks us in for 30 years to an emissions path that doesn't reach the goals that we're all looking for. But how do those who consider whether I should electrify or whether I should put in a gas facility like a cogen, how do they know that, it's okay to put in the cogen, in 10 years, I can just do CCS. That's my way out. Or, the last couple of days, I can just do biofuels. That's my way out. I haven't got a lot of good feeling that there's really any snowball's chance that biofuel cost and availability or CCS at the cogen level, because you're not at a geologic formation where you can inject, and the scale and the cost. Could you give some perspective? Is there a reasonable chance that one could gamble on a cogen, knowing that they could move their emissions to zero and by 2050 or at some path, or is that fantasy?
Well, there was a big discussion about, 7 years about this idea of capture-ready plants, that the idea that we would allow no new coal, for example, unless it was capture-ready. And then there was a big debate about what does capture-ready mean, and at the end of the day, it seemed to mean that, you just leave enough land so that one day in the future you could build your capture plant. So I guess I'm somewhat skeptical that, that a retrofit is going, planning a retrofit, is part of your thinking about putting in a cogen. I would be very careful about that. I think that systems that are really designed in the first instance to accommodate this make much more sense. Whether it's worth putting in a cogen, I think it believes on your views about, where we're going to be 30 years from now, and will that cogen plant be providing, necessary value and valuable services, perhaps not just to you, as a campus, but if you agree with the premise that we're going to need to keep a certain amount of natural gas in the mix to achieve flexibility, that one could think, okay, well, now I'm building it for me, my campus, but now I imagine, well, Boston could, broader Boston area, I could help, with the balancing over that whole area. So I guess that's more how I would think about it. And I really think, as you look at the last 20%, I think that finding all the things that we don't have a good way to electrify, that need to get really hot, that CCS is a good bet there.
But also keep in mind, your cogen is not all that large. Yeah, now you need a pipeline from the Stanford campus to somewhere in Central California to get rid of that CO2. So you imply, and all of that adds cost. So I'm very skeptical for the same reason on retrofits.
Yeah, the same thing, lots of distributed generation, the worst thing kind of we can do is to put out in the energy system lots of distributed generation, even if it's higher efficiency, because that really commits us to lock in, because we're not, from, like the Bloom Energy fuel cell systems, we're not going to be capturing that CO2.
And I would like to stress on that I'm not going to fix this problem with air capture. Right? Because if it was too expensive to capture it at the point, it's certainly no better to say, don't worry about it, I can handle this with air capture. You may end up there, but that was really an economically lousy decision.
I'm going to encourage everyone to be more succinct. Doug, how about you guys?
I'll be succinct. 2 or 3 things. So, Klaus, how do I think about direct air capture versus other options? Maybe just reforestation, perennial plants, things like that, et cetera, in the last 20%. That's just one. So, kind of an engineered system versus maybe natural systems. Or thinking of that. And then, what about this discovery that happened in Iceland for super accelerated, I guess, mineralization? And then what's the state of utilization of, rather than thinking just sequestration, but utilization?
I would think of air capture as one competitor to give you CO2 to close the carbon cycle, either by sequestration or by reusing it, by putting it into the fuel cycle. If you put it in the fuel cycle, you won't have negative emissions, but you could balance the book. It's one player. And the question then in the end, where I can't ever give an answer, it depends on how much does it cost relative to all the options. If you do afforestation, you can put some carbon away. My personal view is, in the short term, engineered capture will have a hard time competing with but then it can scale. Whereas we heard yesterday, if you start putting all the other constraints on biomass, that you may find that it's not as easy. So it also comes down to a lot, will that Tesla actually want to have a methanol fuel cell? Because it now has a 2,000-mile range. Was that economically reasonable or not? And then you have another distributed source. And those economics I cannot predict. But if it's between $30 and $100 a ton of CO2, you're talking between 25 cents and 85 cents per gallon of gasoline. That's what we are negotiating.
Can I do the mineral question? Yeah, about the mineralization. So that was a very nice experiment. I know all of the folks who did that. Well, I want to say 2 things. One is about the surprise. I don't really think there was a big surprise about that experiment. And we do experiments on basalt, like basalt tuffs, which are the glassy component of basalt. Those things react in hours, and we can reduce, plug up the rock, literally within several hours. So I think that the surprise was that if you compare it to sedimentary aquifers, saline aquifers where you've got primarily quartz as the mineral, that there are different kind of rocks where it can happen very quickly. So I think that was really overplayed. The second challenge, and again, I don't want to sound like a naysayer, but to sort of put a practical reality on it. So that scheme basically requires that you dissolve the CO2 in water so that you can have a high degree of reactivity between the water and the rock. So for every unit of CO2, every kilogram of CO2, you need about 20 kilograms of water. So this is something you're going to do in a place like Iceland where you've got boatloads of seawater, and you can do that. So in many places, this isn't really very practical. If you were to inject a separate phase of CO2, the dynamics are entirely different, and the rate of water flow through the system drops almost to 0 once the pores are filled with, say, 40 or 50% of CO2. So the reactions become self-limiting because the reactants remain in place, and basically the reaction stops. So I love the experiment, but I don't think we should all, go off on another major tangent that says that, a bird in the hand is worth two in the bush.
So, Klaus,
Let me-
we have 15 minutes and pretty much everyone in the room has a question. So maybe we can move on.
Let me just one word. First, it certainly shouldn't replace everything else. I agree with you. But I think what I find really interesting is you can start doing this below the ocean floor into similar aquifers there, and then the water is not a limitation. And so you get other options by putting this on the table, and in that sense, I think it's very interesting, and I must admit I'm biased because I helped them get it started.
So, that was a really nice summary of CO2 capture and storage and sort of how we got to where we are today. It seems as if the CO2 capture and storage is reasonably well understood technology. So, what are the top 3 research challenges that face this technology moving forward while we wait for either the regulatory or the carbon price to kick it in?
Do you want to take that, or do you want?
We can share, right? Let me start. I already gave you my skepticism that I think the flue gases simply won't be there to be scrubbed because that I view as a stranded asset. So I would put a lot more emphasis on innovative designs and figure out how to get the CO2 from there. And that will be, from an energy perspective, cheaper. On the air capture side, well, we can do it, but we're brand new. We stumbled into an anionic exchange resin. We are right now trying to find out whether there are other materials which can do it too. And we have some initial leads, but nothing as good as what we started with. But do you really believe that the first time around we won the lottery? Right? So there's lots to be done. There are the environmental, the policy issues. None of that has been really worked out, right? So there's lots to be done on that side. On the other hand, we understand a lot of the other parts quite well.
So on the capture side, I think that the energetic requirements for capturing CO2 using the technology we use today, basically thermal regeneration, are very inefficient. So if you look at the actual work it takes to separate CO2 compared to the minimum work that is thermodynamically possible, it's something like 3 to 4 times bigger. We should be able to do better than that. So, I think that the fuel cell routes are really interesting. There are a number of different cryogenic pathways for capturing CO2. So basically anything that can reduce the energy penalty of CO2, I think, is really important. On the storage side, I think that where we are right now is having the opportunity to observe large-scale CO2 transport in representative formations is really crucial. There are many demonstration projects on the sort of tens of thousands of tons. We have a couple on the millions of tons. Many of those are, though, done by industry, and we haven't had the kind of academic, scholarly work on some of those projects that we would like to, Schleipner being the exception.
Hi, Klaus, I had a question I'd like to ask you, and this kind of gets to this scale issue. So imagine we're capturing CO2 in this kind of diffuse scale with an air capture device. Would you then see that, how would you think about, say, marrying that with a source of hydrogen, for example, to make synthetic fuels? Could this be done at small scale? Would this be large scale? How would you get the CO2 where it needed to be? And has anybody thought about that kind of thing?
It's a very interesting question, and I actually first was not so concerned about the hydrogen, but the sequestration, because sequestration sites tend to be very large. Yeah. On the other hand, I realized if you look at a typical power plant, coal plant in Arizona, and if I were to cover it with 1 ton a day devices to collect CO2, I actually can collect about as much CO2 as that power plant would give out. I can put about a few million tons of CO2 in a square kilometer before actually the transport from the air to the ground is the limiting factor. So you can get fairly large concentrations in one place, but you also have the option to be distributed. And one of the things we're talking about right now and working with is to feed algae. And there we really would like to have a 1 ton a day device feeding an a hectare of land, and then have another, rather than trying to build a sparging system coming from a coal-fired power plant covering 30 kilometers by 30 kilometers. So there we'd like to be distributed. When it comes to solar energy, I think we would match. If you take a few square kilometers of solar panels, we would be small by comparison.
Right, I think that's right. But there are scale economies when you're piping fluids around that are different than if you're running wires. And so the solar case could be different there.
Right, but
moving material.
we naturally distribute, and so where the optimum is, my own prejudice is I like to get stuck at the ton a day because that's one container, and I can deliver that over the road where you want to be. Nothing prevents us from saying we build a 300-meter tall structure, and then we have, of course, a lot more CO2 on a site.
Thank you.
We're going to move into our rapid round of questions, if we can.
So we do have a lot of strained assets currently that will go away in the long-term future. But in the meanwhile, I'll be curious, what are the areas where we should indeed start that large experimentation? China seems like a possibility given the very recent build-up of coal, so that strained asset is going to be there for a long time. But could you comment, like, where should we start? Where should we have that experimentation?
Well, I think that California should look at a large-scale CO2 capture from natural gas plant and carefully think about how the operations of that gas plant with CO2 capture can operate in the flexible and dynamic way that it needs to do to balance the very, very high penetrations of renewables that are expected in California. So I think that would be a great place to start. China is actually doing a lot in this regard, and they make a lot of sense to do that. They're doing it on some, on basically coal to liquids plants, and as somebody said, that's not a good idea to do because you end up with sort of the double whammy of emissions. But so I think that I would love to see Germany do this, but that's not going to happen. They don't favor CCS.
Sally, I think if Chris Clack took his model and doubled the price of natural gas in it, so you're saying that CCS would roughly double the price, or 1.5. I think his model would find a pretty low-cost solution to the electric sector. And the gotcha there is the capital cost of CCS, so that you can't afford to run it just a few % of the time. And so is there any potential for low capital cost separation technologies?
I don't think so, and I think that if we can't figure out a market for something that's crucial for keeping the overall system fully functional, I think that's the wrong way. I mean, this idea that we would, create an asset that we would run 1% of the time, that's crazy. You have to make a business model that values it on a daily basis. I mean, otherwise it's just not going to happen.
So the idea of CCS on gas peakers,
Yes. I would suggest something else for him. I would say, first I would ask him whether his turbines could, in a pinch, run on hydrogen, and make that hydrogen in a fuel cell and give it back to you. But then my main goal with that fuel cell electrolyzer combination, which because it does both, has actually a fairly high utilization, would have the advantage that it, most of its time, spends adding a CO2 to that hydrogen and sells you transportation fuel. And if you really deal with seasonal storage, then we can start discussing, was it cheaper to have a big methanol tank, or was it cheaper to have a hydrogen tank? And I think the economics of the year 2050 has to sort this out. I'm not qualified to answer this. But in that system, you have the way to run your peaker from a gas which is made from renewable energy when you have too much.
So I want to go back to a study that was done in Germany, and actually it was a comparative study of Germany and California. And they asked the question of what was the value of dispatchable power on the overall energy systems cost. And they concluded that if you had about 20% dispatchable low-carbon power, which CCS could provide, that the overall system cost was about, I think, 20% less in California, about 50% less in Germany. And so again, I think the premise that you want to fill up the stack with everything that is a renewable resource or a non-dispatchable resource is probably the wrong way to think about the problem, which sort of goes back to why I asked you, well, if you could figure out what was an ideal, gap-filling technology where you allow the full system optimization, at least the study that was done, it was a German study, really said that you needed dispatchable power. Their dispatchable power was, I thought, kind of silly. It was solar thermal from Africa to Germany. That's a big stretch. However, in California, the idea of solar thermal, which allows you the shifting of the power to nighttime, would be helpful. But again, CCS, a gas plant plus CCS could play that role.
So I'm going to try to maybe get a little more specificity to what I think was Ken's question. If you did have a gas plant that was used in dispatchable mode in something like Clack's scenario, that's used 20% of the time to fill for intermittent renewables at whatever level you have. Two questions are, if you add CCS to that gas plant, how much does it increase the cost of gas because you're not now fully utilizing the capture part? And the second related question is, have people thought about if you do that, how much pressure or other management you would need because the periodicity of the emissions may not at all match the need for pressure management optimally of the reservoir, and so you have flows to deal with. How would this actually play out on cost, added natural gas if you implemented CCS, if we're dispatchable and only utilize 20% of the time?
Right. So let me answer the second question first because it's a lot easier. So on this idea of pressure swings, that's not a big deal at all. That's no problem. On the economics of a plant that is only operated 20% of time and the big capital investment, I mean, if you look at it that it's competing, at really cheap prices, I would almost say that, well, you just have to value that service that provides, and compared to the alternative, which would be more transmission, more generation. So, and I don't know the precise number, but yeah, I don't.
Coal is 30% roughly, but that's base load. And then this is not base load, and the question is how much.
Right, yeah, I don't know. We should calculate it. Yeah.
Sally, just on the advanced power cycle point, this is kind of maybe a factual foundation point. Are you following Net Power's technology, the alum cycle, and what do you think of it? I mean, it seems to be an important development because what they're claiming is they are using back-end CO2 from a natural gas combustion turbine, compressing the CO2 anyway to have to put it back through the turbine. So you've got free separated carbon and compressed carbon, which then the remaining costs are really only injecting underground. And I think they're saying a price point of delivered zero carbon gas power, 50 megawatt demonstration being built right now near Houston at something close to the cost of unabated gas right now. So curious, does that seem plausible from what you've seen, and is it a game changer?
Yeah, I mean, I think it sounds very, very interesting. I think it's exciting how well it actually works, and I mean, to design a new gas turbine, with different fluid, and those are really a big deal. How quickly and effectively it will get up to scale, I don't know. I'm delighted that they're doing it.
So we have on exactly this point, many years ago I got hit. You can't possibly design a new gas turbine because it costs billions of dollars. We are dealing with a multi-trillion-dollar problem. If we think it needs a new turbine, we should design it.
Yeah, and if a company like GE or one of these kind of Siemens, if they get Yahoo.
Toshiba's all in on this one.
Yeah.
Great. So we're over time. We have 5 questions left. I'm going to propose we try to get through them very quickly. Okay, great. So I'm sorry if I missed this, but I was just curious about the resin that you talked about, the material that you would be using and where it comes from or how much of it you would need and whether there are limits on
Well, it's an anionic exchange resin, which is currently used in water preparation, so where it has lifetimes of about 10 years, 20 years, depending on the application. They are pretty tough. They have quaternary ammonium ions as the fixed cation to the polymer, and you can make them in the carbonate form or in the hydroxide form. We swing between the carbonate and the bicarbonate form. The stuff is made already by the truckload, and the cheapest I can get is around $1.50 a kilogram. So that enters into the cost. Right now we have a 1 hour cycle. I suppose one could make that a 10-minute cycle. That depends on how finely you grind it. And then an unload cycle, which is comparable in time. So.
I want to ask Klaus a question. So is there any way you could combine your system with something that also scrubbed traditional air pollutants, so you'd get the co-benefits that would be, at least in the short term, far more compelling?
We would scrub NOx and SOx. We don't like it, but because it turns out we have tried it. What happens is, because it's an anionic exchange resin, every 1,000 cycles I have to wash it in a sodium carbonate brine to get rid of the wrong ions. But beyond that, nothing much happens. So that we can do, but it gets hard because they are more dilute, and so it actually, you can sell it as a side benefit. At some level they interfere, but not so badly that we couldn't deal with it.
So just a quick question. So can you talk a little bit about physics limitations or cost limitations of CO2 transport, by presumably pipeline transport or something?
Yeah, right now we have about 5,000 miles of CO2 transport pipelines in the United States. They're operated routinely. Typically, if you're transporting CO2 on the order of up to, say, 100 kilometers, that it adds maybe $2 per ton of CO2. So it's really not a technological issue and not a cost issue unless you're really going across the country. And there are gigantic economies of scale if you ever imagined there was really an infrastructure for CO2 disposal.
Yeah, I sort of imagine that in the context of this intermittency problem, in the same way we talk about scale.
Yeah. If you do air capture, of course, you want to do it where you want the CO2, because the air mixes fast enough, so you eliminate the transport, except on short distances.
I wanted to ask about something that's at the nexus of the stranded assets issue, the lock-in issue, and kind of the relationship between the first 20% and the last 20%. And it concerns the possibility that all of the CCS technologies provide an avenue by which companies with traditional expertise in oil and gas can be part of the solution rather than part of the problem, potentially enabling us to move much more quickly into the area of getting the first 20% out. And I guess the question is there really a serious concern that once we start utilize some of the expertise of the traditional oil and gas industries, we really have serious lock-in, or can we envision an energy future in which these technologies just continue to operate through the century down to the last 20%?
Yeah. My views on that are that, if that were to happen, if the oil and gas industry were to start playing a really major role in the CO2 climate problem, that the long-term play for them is basically CO2 neutral fuels, or it could be nitrogen fuels. So they're excellent at refining. So I see an evolution from capture and storage to all the way through something that involves not mining underground carbon and putting it back in the air.
Okay, a techno-economic question. So Sally's mentioned a couple of times this fuel cell energy project, so I looked that up. And so it appears that the core of this is that the molten carbonate fuel cell is the only fuel cell technology that actually uses CO2 as a fuel. And so that's the attraction. So normally you use natural gas and you reform it to CO2 and then use the CO2 as a fuel. So if you had $100 a ton CO2, and now you can bypass the cost of reforming, and you now send that into a molten carbonate fuel cell, how does that work out? Has someone looked at that? Because that seems, yeah.
Well, the molten carbonate still uses CO2 as a carrier, not as a fuel, right? Because it's at the bottom end of the energy scale. But solid oxides, for example, can electrolyze CO2 to CO and go backwards. The molten carbonate needs to carry a carbonate ion to carry oxygen across. So it's not really.
Well, Wikipedia isn't always right, but if we're looking at it, the CO2 is actually cheaper carbonate ions, and that's
It's not the energy source. You have hydrogen. You have hydrogen reacting with the oxygen, and there's a CO2 being freed.
Yeah,
Or in the reverse, you carry oxygen ions as carbonate ions, and you have to deal with the CO2 which comes along for the ride. Right?
So the current version that they're proposing is to use methane as the fuel source, and then CO2 flue gas for migrating the ions across the fuel cell.
Last question. Great. Very quick question for Klaus, and I apologize if it was covered while I was dropping my son off at camp. The Navy has looked at extracting CO2 to use to make syn fuel, and they've done studies. They've concluded it's easier to get it out of seawater than out of the air. And Ken told us that the sea is equilibrating quite quickly, the oceans with the air. Should we focus on seawater extraction?
I think it's an interesting discussion. I had the discussion with the people who do this, and it comes down to being a matter of opinion. Because it's touch and go both ways. I believe the hard part of the separation problem is to separate the molecules from each other. And in that case, the air is 10 times better because there are 2,500 molecules of other air for every CO2, and that puts you at 2,500 to 1, whereas in the ocean it's 25,000 to 1. But on the other hand, if you say, how much do you have in a cubic meter or in a liter, the ocean is 100 times better because the air is 100,000 times as dilute. I believe it's the separative cost and the fact that it's more concentrated doesn't really help you. They believe the concentration helps you. So it depends actually on the details of your separation mechanism, who is right. And I think you can place a bet on both and see who will come out in the end. And I placed my bet on one way, they placed it the other, and we'll see what happens.
All right, maybe we can give the speakers a round of applause. So the organizers noticed towards the end of the day yesterday that people sort of felt like we wanted to start doing some synthesis and pulling together what we've heard, knowing that we still have yet to hear from some folks on wind and nuclear, which we'll be getting to shortly. We've got about 20 minutes now, and we thought maybe a useful way to frame this next 20-minute discussion would be to ask you all if you have ideas of things that are clear game changers in some sense in getting this last 20% decarbonization. And I mean specific technologies, for instance, low capital cost electrolysis is one example that we've heard come up a couple of times. So people have ideas about game-changing technologies? Floor is open.
Well, I want to second the low-cost electrolysis concept, which has been mentioned already, but also this carbon capture technology that was also just mentioned. I think it actually could be a game changer. These electrolytic means that also provide a co-benefit of electricity, for example, but also new cycles for power production, fuel cell technology, for example, that could use natural gas coming in and at almost no cost of capturing the carbon if you do the right kind of anode recycle and things like that. There are these kinds of new power generation technologies that are super amenable to the carbon capture and storage. And finally, the solid oxide electrolysis coupled with a heat source. Okay, I mentioned that in my comments too. I really think it can magnify the benefit of dispatching these dynamically and just storing heat to give you the extra hydrogen. They're storing heat to give you the extra hydrogen. You can get that heat from other carbon-free sources like nuclear power or concentrated solar.
Thanks. Anyone else? Klaus? Yeah?
Well, I believe it's important to look at where we really have bottlenecks. And what I was trying to say earlier is we really need cheap electrolysis. And I'm agnostic of whether that is an SOEC, a molten carbonate, or a PEM, or an alkaline. But we really need to make that work, because then we can couple, which we never could do, the fuel side of the world with the electricity side, and we can have that dream we just laid out. I do believe that BECCS is critical, or put it differently, air capture, to close the cycle. And BECCS is one option, and the technology is another. And having that on the table, from my perspective, is important. Lastly, we see over and over and over again that capital costs are what's killing us. And I often think the numbers are not as well determined as we think. And to Steve, sometimes you have a good argument a little later. You said that chlor-alkali, and clearly it's mass-produced and big, and therefore it's as low as it could be. The example I always had is coal between 1985 and 95, at a very well-established technology, dropped its cost by a factor of 2 because it had to, because natural gas was nipping at its heels, and it was either die or cut your cost in half. And they did, which tells me that we really don't know what things cost until we get pushed, right? And so here, don't put too much emphasis on your current cost understanding, because things can happen. And so we need to push at capital cost in general. And that's where I come in with the mass production approach.
I'm going to go around this way. I'm not sure if you guys were first.
Thanks. You know, I've had a really important insight at this meeting, and I think it's that the concept of a game changer isn't a particular technology, even though we've heard lots and lots of attractive options. I think the concept of a game changer is what kind of technology suites or process suites work together to provide a compelling system framing for the pathway to this last 20%. And in particular, I think this concept that many people have discussed is the many sources of input and many sources of output for particular technologies is especially attractive. And I think that the four things that we've heard about a lot that fit together in a compelling way is in some ways the game changer rather than any of the individual technologies. And those four things are electricity generation, production of hydrogen, storage of heat, and CO2 removal. And the opportunities that are represented by each of those are embedded in the particular technology. Where they really come into focus is that for each of those, we have a number of compelling opportunities, and the end products of each can go into a number of different places that help us toward the last 20%.
I'll just reiterate the importance of thinking about systems and cycles and pathways toward the molecules and the processes to get that last 20%. I think that's absolutely critical. I think to Chris's list of 4, I would add either synfuels or biofuels for that chunk of the transport sector, which seems to be so challenging, which would put us up to 5.
I'd just say fairly self-servingly that you've sort of discussed and suggested that we need power CCS and these sorts of things and novel cycles for power CCS, but not to forget industrial. That's even harder to decarbonise in some ways. There's no alternatives.
Sorry, just on that one, because it hit me during the cement conversation that we need a breakthrough in terms of finding decarbonization paths for creating cement. So, anybody works on different research?
Yeah, I mean, there's quite a lot of people working on different cement, CCS technology.
Without CCS, sorry, I'm just asking the non-CCS guy.
Yes, but mainly for lots of
Okay, sorry.
I don't want to make air capture solve your problem, but if you can say air capture is less than X, then we can figure out, then we can have you survive. If you then can figure out how to get better.
I know we're supposed to be focusing on technology, but we have a combined policy / technology one, and it seems really critical to get real-time, real pricing of electricity through to the consumer and industry, so that that demand can be responsive to real-time pricing, because otherwise, to get that last little bit of reliability, you're going to be building something that's going to essentially get used some tiny fraction of the time.
Just a small friendly amendment to Jack's for the fuel cell cycle is interesting, but again, the reason I put net power on the table is it's a fairly conventional technology that's a little bit of a horizontal nudge, instead of a whole major system. So.
Yep. I'm shocked there's no cards up right now. No one has any? It's the first time we've had that problem.
My comment is very short. Energy storage.
So we haven't talked about it yet, but I guess it will come up next. The small modular nuclear reactors as a potential contributor that we haven't discussed yet.
Per agrees with you.
Hopefully we'll get into the details of that.
I might echo Chris, but let me just be specific. I think it's not the individual technology that is the issue, but developing capabilities that give us optionality to fill these gaps is what we should be shooting for. So we're not picking favorite technologies before the marketplace can develop, deploy them. And so I see still that this coupling between the electric sector and the fuel sector is something where capability needs to be developed with lots of optionality. And whether or not you're electrolyzing water to hydrogen or getting it with solar or doing something else, we've got to find a way to couple the electric sector to the fuel sector, because most of the energy on our planet is stored in chemical bonds, and the quality of energy you get from doing that in certain applications is, like transportation, is not found in any other way, and the same thing in energy storage. And so I think we've got to find a way to couple those two things, and part of the reason that people are here is to get them out of the stovepipe of just thinking about the electric sector or the fuel sector and talking to each other. So that would be my number one capability to be developed without picking any favorites on it.
So being the facilities guy, as it were, I think the technologies that will enable us to also get to the first 80% that have a dual benefit are needed, because it's 2015 and infrastructure is being built all over the place that's burning natural gas and nobody's listening. So, biofuels and carbon capture, otherwise by 2050 it's, we've missed the opportunity. This last 20% isn't going to matter. So if carbon capture and or biofuels could really be accelerated, then we can get out of this mess of everybody continuing to deploy more and more natural gas infrastructure just constantly. It's unabated. It's accelerating. And electrification isn't going to happen in these people's minds. They don't care. So something's got to be retrofitted after. That either feeds them clean fuel or puts a scrubber on the end, because it's too late if we don't. There's just the last 20% is not going to matter.
A question. There are a huge number of countries globally that are already deeply decarbonized, and it's because they haven't yet grown their economy. If we think about game changers for deep decarbonization, what could that look like for countries that just ideally should stay where they are at the same time that they grow their economies?
Mine is on developing countries, so I think that a lot of the CO2 emissions are not going to come from the US, but will come from places like China and India, where they are willing to put in coal. And so the technologies that we have to develop must compete with coal in a lot of these places. And so things like nuclear, or it's essentially our job to show that it can be cost competitive with coal and they can still have economic prosperity for all their citizens.
So I apologize for missing the morning session. I have this pesky thing called another job. And it involves DOE, so you can put that together. So on the subject of game changers, a game changer I very much strongly believe in, we're going to need to continue to make stuff. And so if the process of making stuff, whether it's cement or steel or manufacturing or water or whatever it is, if we can really start thinking about those as processes which need to be controllable, flexible loads, large controllable loads of, you know, electricity when it's there, hydrogen when it's there, creating other products when the others aren't needed. Just how do we, the kind of that last 1/3 of the economy that's not transport, not power, how do we imbue that with more ability to support the low carbon needs of the other two sectors?
One more aspect of this systems integration component, I think that at this meeting we have tended to think about the decarbonization problem as a power generation problem, but as Ken's already indicated, that it's also a demand-side management problem and a grid integration problem. And I think that recognizing that the whole thing, the power generation, demand-side management, and grid integration is one problem, not three, we're going to be much farther toward the breakthroughs that we need.
Okay, so I think that the electrification of everything we can possibly electrify is really important. And if we think about that context, we want a highly reliable electricity system. And I think that large-scale nuclear, not just small modular reactors, are a really incredible, important component. And if we look at making things like hydrogen, or if we look at making things like carbon-based fuels from decarbonized electricity, that if we can find a way to operate them 24/7 so they fully utilize the capital assets, I think that will make the economic prospects for doing those things much more attractive. And I think technologies like nuclear can help towards that highly reliable 24/7 power supply.
I agree with you, by the way, and I think nuclear is an important player in the overall game, but ultimately the economics has to work out, and right now nuclear looks expensive. But I wanted to put another gotcha into this discussion. If climate change starts hurting, which it will sooner or later, once it starts hurting, we start doing all of this, and oil will get dirt cheap. And the same is true for coal and gas, because they will be under pressure, and they have enormous overcapacity, and we need to figure out how to deal with that.
Great. So actually my comment was going to be similar to Brian's, but I just thought I would interject something too as we think about dispatchable load sources. I guess right now we have a power system that is, built to be very reliable, and we have a substantial reserve margin that we've built on top of the amount of power that we need. And we don't run that reserve margin because it requires fuel, a lot of that reserve margin, if it's natural gas, oil, coal, whatever that is. But it's not that it's not there. So if we kind of turn around the way that we think about curtailment, by saying, okay, right now we're essentially curtailing all of that reserve power, but we're just not feeding it that fuel. But if we move into a system where we have higher reliability with assets that are only available part of the time, but they just happen to also be producing more during certain times, that's actually kind of an amazing thing. I mean, that's almost like you can think of that as just free, low carbon energy available to sort of use for these dynamic load kind of opportunities. So trying to turn around the way that we think about curtailment.
Steve, it may not be fair for me to get a second shot here, but the gotchas, I spent 12 years of my life working on demand management and energy efficiency, so have some scars on that. The gotcha on this demand, thinking about demand as a major knob for the last 20%, my caveat is that I feel like some of the conversation is like, how do we redesign our stuff making system to serve the energy system? And I think the politics of that are very, very difficult. India wants to build a textile industry, you're not going to have a reasonable conversation about how can they do it at, kind of variable capacity and letting people off when the wind isn't blowing. I mean, that's a little bit of a cartoon, but I do worry that that thinking about that, tweaking the demand knobs really hard. Those are very sticky industries, very complex, and there are all kinds of other vectors. The political people don't necessarily want to think about, again, having, the loads serve the energy system. It's usually the reverse.
Yeah, I think that's a good point. And we've heard that some of the integrated industrial applications with power and things like that are also huge policy challenges and incentive challenges.
I want to go back to what we mean by this last 20%. I think I brought this up a couple days ago. And this is going to be a vague concept, or a vague comment, so accept that for what it may. So another way to think about the last 20% is that we have a carbon budget that we have agreed to, and that we are within 20% of this carbon budget. And if we think that our job is not to, in any sort of daily stack of energy demand, try to reduce that 20%, that last 20%, but really think about when the world realizes that it's only got, another, couple, 5,000 gigatons that it can emit, and then we're done. If we reframe the last 20%, in that context, would we be saying things differently, or would we be thinking about things differently than sort of your mental model for this? I mean, certainly it brings a sense of urgency that wouldn't necessarily be there if you thought about it the other way.
Yeah, maybe Ken, and then we'll get to you.
I guess just there might be subtleties of how these different framings would change things. I mean, essentially we're saying, how do you get to a near zero emission economy, an energy system, and I don't know. I don't see how big. Down that we as a global society really think we're on this countdown, and there's a real target, and I think it's a different psychology that it brings to how you would think about it. I'm going to hand it to Jessica now that I have control of the mic. So okay, we had something to say.
Oh, sorry. Sorry about that, Ken. So I mean, I think what you're getting at is that industrialized nations, richer nations, would have to reach 100% much sooner, and the last 20% is actually, at least that thought came to my mind. The last 20% is actually represented by, other non-industrialized nations or emerging economies today. Changes the solution potentially.
All right, Klaus.
Yeah, I 100% agree with you, and I actually try to think about it this way. We have a budget, and the only problem with that statement is we don't quite know what that budget is. And if you say it's 1.5 degrees, I'm not so sure we aren't already over it, right? Because if you just let the planet warm up from 400 ppm for the next 60 years, we may be past 1.5 degrees. At least we're not far away from it. So if you take that point of view, we are talking right here and now about the last 20%, and I think we fundamentally make a mistake by viewing these as annual outputs rather than a total budget. And this is a waste management problem at the end, and we may already have too much litter in the atmosphere that we can tolerate, and maybe we can tolerate 450. But if you think about it that way, we are in the last 20% because we started 200 years ago.
So I think I'm going to let Chris maybe have the last comment, and we'll have some more discussion a little later. We're into coffee time, so yeah. But we will have a follow-on discussion before lunch.
Yeah, thank you. My comment is not really a gotcha. It's kind of changing the way people are thinking about it. So if you look at just electricity at the moment, 36% of the capacity provide 4% of the energy. And that's today before we've decarbonized it. And so there's a lot of room for improvement from the demand side, but that will then play into the hands of less dispatchable needed, but also more renewables can be used. But the thing that I run into the most when talking to developers and people that are putting things on the grid is trying to convince them that putting more value to the grid rather than immediate profits from their highest capacity factor locations is a hard sell for them. Because if you try to say to them, well, actually, you are going to get more money in the long run using this higher value location than the highest capacity factor value location, even though that's not technically a technology, that really is what's driving a lot of the deployments at the moment. And if we can't move away from that, we're actually going to find it harder and harder to get to these really high penetrations levels way above 80%. And I know that's just electricity, but it will circle round to all the other sectors as well.